talked about obviously exponential growth at a certain percentage, either growth or decay. This unit, what we're adding in today is what we call continuous growth, and we'll define that a little bit better later on. But what we need to start off with is just a quick review of the number e. The number e is an irrational number, similar to pi in that it doesn't repeat and doesn't end. We typically use 2.71 as the decimal approximation of e. What we'll look at is using e as a base of an exponential function. What we call this is the natural base. And those of you that move on to calculus, you'll see this used in a lot more situations than what we look at, okay? What you need to know is that an exponential function with a base of e represents what we call continuous growth. So if you are told that something is growing or decaying continuously, we need to be using base of e, okay? Any positive base b, which is what we've had so far in our exponential functions, can be written as a power of e. If the value of your base is larger than 1, then this exponent k is positive, meaning if k is positive, then we have exponential growth. If we have exponential decay, where b is between 0 and 1, then the value of k is negative. And we'll look at some examples of this in just a moment. So what we are going to do, and it's already pretty much done for you, so just kind of follow along here. What we're going to do is start with our general exponential function that we've been working with all along. Okay, q equals ab to the t. That should look very familiar. What we are doing is substituting e to the k in for b. Okay, we said that b equals e to the k. So I'm going to substitute e to the k, bless you, in for b. So that then gives me a times e to the k to the power of t. We can simplify this up a little bit and say that q equals a times e to the kt. A is still your initial value. A is still your initial value. That has not changed at all. E to the k is your base, and then it says below, constant k is your continuous growth rate, okay? K is your continuous growth rate, and of course t is the amount of time that you are growing or decaying. In general, then, the continuous growth rate k we found is given by solving that. If we substitute all that in like we just did, then for a continuous growth or decay function, q equals a times e to the kt. I feel like I'm repeating myself, but if a is positive, which we've seen all along, we've had only positive initial values because we haven't been starting with a negative amount of money or a negative number of people in a population. So this is not changing. And k is greater than 0, then q is an increasing function or exponential growth. and vice versa. If k is less than 0, then q is decreasing or exponential decay. All right, all we are going to do on these next 3 examples is give the continuous growth rate from these 3 functions, okay? So this is just getting you used to the different notation. Remember that k is your continuous growth rate, and this is in decimal form, okay? So that value of k is your growth rate in decimal form. So if you look at this first equation, notice that your value of k is 0.2. That translates to what growth rate as a percentage? Yeah, just 20%. Okay? Don't overthink this. Is just, like I said, getting you used to this different notation. So what would the growth rate be for the next one? 30%. And the last one, negative 20%. So what does this function mean? Or what does that negative 20% mean, I should ask instead?
It's decaying.
Yeah, exactly. That means that this is decaying. So it decays continuously at 20%. Okay. All right. Let's go ahead and look at this first problem. It says caffeine leaves the body at a continuous rate. So I'm trying to highlight everywhere we see continuous rate. It's really easy to overlook that, but we need to be really careful that we don't, because it's a completely different type of function that we are going to write when it's a continuous rate, okay? Anyway, caffeine leaves the body at a continuous rate of 17% per hour. How much caffeine is left in the body 8 hours after drinking a cup of coffee containing 100 milligrams of coffee? So we first want to write the function to model this, and because it's a continuous rate, I need to use a times e to the kt. So what do we know that we can substitute in here for this specific model? Haley, I'm sorry. Hallie, gosh.
It's been 8 hours of time.
Not yet. Don't use the 8 hours yet. I just want the general model.
17%.
Okay, it's leaving my body.
Okay, decreasing.
So how does that work in terms of K if it's decaying? No. Okay, go back to this last example up here.
Oh, so negative 20.
Exactly. So this works a little bit different than how the regular ones do. Okay, it's not where we take 100% and subtract it. It's actually a negative exponent. So we have e to the negative 0.17 t, but I'm missing something. What is a? 100. 100 e to the negative 0.17 t. So now using this model, now we can find out how much is left after 8 hours. So at that point, what?
Sorry. I know you're drawing for a second. I was like, what are you
That's an arrow.
drawing? I'm not sure what was going on with that.
That's an arrow. I know, I'm really good. Haven't I ever told you my lowest grade in all of 4 years of high school was in art? Like, legit true story. Art class.
Good.
Like a B. But that was bad. So I'm plugging in 8 for T. On your calculators, I would grab your calculator and do this with me so you know how to calculate this on. I was grading Algebra 2 test last night, and I had my calculator out, and Garrett walks up and he goes, "Mommy, what is that?" And I said, "It's a calculator." And he goes, "Can I play with your calculator?" It was so cute. Calculator. I was like, okay. Okay. If you go second ln, which is in your very left-hand column, second natural log, you get e to the power of. So we want to calculate the exponent first. So e to the power of negative 0.17 times 8. Hit enter. And then multiply that by your initial value, the 100. I think that's the easiest way to enter all of that in your calculator. I guess you could do it all at once, but people just don't use parentheses correctly and you get wrong answers. So we're seeing 25.67, and that's milligrams of caffeine.
I keep getting the error on it. I'm probably just typing it in wrong. That's right.
Oh yeah, I can't see what you did. Delete it.
Oh.
Try it again. All right, second question. Estimate how long it takes for the amount of caffeine to be reduced to half of the original amount. If the original amount was 100, I'm looking for how long it takes to get to 50. Exactly. So I'm still using our general model that we wrote, and I'm looking for when C equals 50. So we can do a similar thing that we did last time. So plug in your original model here into your y equals. I'm trying to get it so you guys can see that well, and I'm having trouble. So 100 times e to the negative 0.17x. And then I'm looking for when y is equal to 50. Okay? You're probably not going to see anything if you're on your standard viewing window, so I go zoom 0, which is zoom fit. Hopefully that will fit our window to our two curves. There we go. That's pretty nice. And then use your calculator to calculate the intersection like we did last time. So if you need a refresher on that, that second trace is your calc menu. Number 5 is intersect. Recall that it will ask for you to hit enter on your first curve, on your second curve, and then for you to guess where the intersection point is. Samantha?
My line is just like, or my graph is just two like straight lines, like on top of each other.
Okay, I'll have to look at yours. I can't diagnose it since your calculator's different. Remind me when we're done. So I'm seeing that the intersection point, or that when y is 50 for both of these graphs, the x is equal to 4.08. So what does that mean in terms of our problem? What does that mean? In a sentence, what does that mean? Write a sentence for this. Let's translate this number to have some meaning here. Gabby, what you started with was fine. I just want a complete sentence that explains what this number means. Gabby? Yeah, you had it started okay. I just want a complete sentence to explain.
4.08 hours for the amount of caffeine to reduce to usual.
Very good. It will take, we'll say about, because it's an approximation. It will take about 4.08 hours to reduce the amount of caffeine to half of the original. Good. All right. We are going to come back to our continuous growth and decay. But what we need to start, or what we need to talk about first is compound interest. This is something you've seen before, you saw in Algebra 2, but this will lead us into what we call continuous compounding, okay? What I want us to do is calculate your bank account balance at the end of each year for these two situations, okay? We deposit $1,000 into an account that pays 12% interest just once per year, okay? So this is taking our initial balance times 1 plus our interest rate. Okay, so go back to day 1. If you calculate that out, we get that our balance is $1,120. But what if we do this? What if we take this 12%, divide that up into 12 1% interest payments? Does that make sense? So take that original 12%, and instead of just taking 12% one time, let's split that up and calculate that 1/12 of it every month. So we would still have the 1,000, but what's our growth factor each time?
1.01.
Yeah, so in this case it's 1.01. And how many times are we multiplying it by that? 12. Good. So if you do that, 1.01 to the 12th times 1,000, we're getting a little bit more than situation A. Why is this different? Because I'm still using 12% interest, but why is this different? Why are we getting more money with the second situation?
You're getting money more often.
What do you mean?
Is it happening more often with the interest? So,
The interest is being applied more.
Because it's monthly, you have the interest from the previous months on top of regular.
Exactly. You're earning interest on previous interest amounts. Whereas this first situation, you're only earning interest off that principal amount that you had. But here, like she said, we're earning interest on the interest. Okay? When you do that, when you earn interest on previous interest, I feel like I've said that word a million times in the last 1 minute. This is what we call compounding. That's what we call compounding. Which brings me to what we call a nominal rate versus the effective rate. Your nominal rate is your annual percentage rate. So this would be the 12% in that previous example. This is the rate without any compounding. This is your rate without any compounding. The effective rate, however, tells you how much interest the investment will actually earn. This takes into account the compounding. The fact that you're earning interest on interest. Sometimes these are the same, sometimes they're different. And we'll look at when they're the same and when they're different here in just a minute. The general compound interest formula that you guys have seen before B for balance equals the principal times 1 plus R over N to the NT. Note that R is your nominal rate. N is the number of times per year that you are compounding, and then T is the number of years you have invested. Okay. This portion of the formula will give you your effective rate based on the nominal rate R. Okay, I want to do this example before we go to lunch, and then we'll come back and finish the rest of this up, okay? So this says, what are the nominal and effective annual rates for an account paying 3% annual interest compounded annually and quarterly? So this is really like two problems. So let's split this up. Let's look at doing it annually first. So the 3% annual interest, that is your nominal rate, regardless of how often you compound. That annual rate is your nominal rate. It's just another name for it. All right, if we use this part of our compound interest formula, we can find the effective rate. So I'm going to take 1 plus, I'm just kind of following this, my R is my nominal rate in decimal form, so 0.03. N is the number of times per year that I am compounding. If I'm compounding annually, I'm only compounding once. And this is to the N. Those two numbers are always the same. And we're only doing this for 1 year. So if we go through and calculate this, 0.03 divided by 1 plus 1 to the power of 1, what do you get? 1.03. If you change that back into a percentage, what is it? 3%. Change it back into a percent.
Oh.
What did I say decimal?
No, you should.
Oh, okay. Yeah, that's what I meant. 3%. So here's the deal. We actually didn't need to go through all of this, but I wanted you to see what happens. If you are only compounding once, your nominal and effective rates are the same. Okay? Because there's no difference in the number of times you compound. It's when we compound more times than one when these are different. So let's look at doing this quarterly. Your nominal rate does not change. That's still 3%. It's the effective rate going to be different now. The more you compound, or the higher your effective rate is going to be, the more money you're going to make. So let's use this again. So 1 plus 0.03 over 4 to the 4 times 1. We're only looking at doing this for 1 year. So let's do this on our calculators. 0.03 divided by 4 plus 1 and then to the power of 4. What do you get? What do you get?
I got 1.03.
Yeah. When you change that back to your percentage, your effective rate is 3.03%. So you're making just a little bit more money when you compound quarterly like that, okay? All right, when we get back from lunch, we will finish this up.